Hello, my name is Radi, and in this first section I will talk about the concept of information, as transmitting and receiving signals is our main goal. So, let's get started. Although we have a common sense of what information is, it will be nice to have something a bit more formal. Without going into broad mathematical explanations and definitions, I will just give some basic sense of the ideas and concepts. The major question here is what information is and how do we quantify it. You may stumble upon some very broad philosophical answers, but we are only interested in the engineering problem of reproducing as closely as possible a simple message. This message, of course, has some initial form at some starting point. It has also a meaning, and this meaning is with respect to some, for example, language, coordinate system, etc. But we will not care about these. For us, information will simply be an element from a set of possible elements which we must represent as closely as possible. What do I mean by that? Let's take an example with 3 questions and try to answer in which case we receive information. The second task with this example is to try to determine is it possible to quantify information. For that purpose, imagine you are the emitter of the message and the other person is the receiver of that same message. So, first question, what if you tell someone something he or she already knows? How about if you tell someone something that he or she never thought possible? Or imagine you tell someone something he or she suspected but weren't sure about. So, in the first scenario, the receiver hears something he already knows, so we can conclude that there is no information received. The second scenario suggests that there is received information, while in the third scenario, the receiver hears something that is suspected, and we can say that he or she receives confirmation of something suspected. So, it is more or less easy to say if we receive information, but how about quantify it? With these examples, we can conclude that it is hard to quantify units of information. And this is because we cannot definitely say in which case we receive more information. But we can conclude that if we receive something that was previously unknown to us, it is information. So, as an example of the last statement, consider the English language. There are 26 letters in the English alphabet, and so there are 26 possible one-letter words at most. How about two-letter words? Allowing for repetitive letters, there are 26 times 26, which gives us 676 possible two-letter words. Continuing this logic, we can calculate the amount of the possible three-letter words, and so on. Of course, most of those are not real words, but this is the upper maximum of combination for 1, 2, or 3-letter words in a language with such an alphabet. If we consider the longest word to be 45 letters long, then we just need to add all the possible words from 1 to 45 letters long to get the maximum possible amount of words. And that number is many billions of times more than the amount of individual sand pieces on our planet. But still, it is finite. It is important to mention that concept, as going even further, we will start to see a word as a single element of the set of all possible words. And if we extend that logic, we will start to see a message as a single element of a set of possible messages. Finite once again. Then we can use this total number of messages in the set or a monotronic function of it, so it is reversible, to define a function which tells us how much information has been produced when we choose one specific message from the set. For that purpose, using a logarithmic function seems the most natural choice as the base corresponds to a choice of information measuring units. For example, if the base is 2, the resulting units are called binary units or bits. The word binary comes from bi meaning 2. A single binary digit like 0 or 1 is called a bit. For example, 11010 is 5 bits long. The word itself is made up from the word's binary digit. Now, having that clear, consider having a much smaller alphabet consisting of just 2 bits, each of which can only take 2 values, 1 or 0. We can model this with two light bulbs. A light bulb which is on is 1 and a light bulb which is off is a 0. So there are just 4 possible words with this configuration. So imagine that our lights are in the state 0, 1 and we can see them being in that state. Do we receive information? The answer here is no. But imagine that we have no idea of the state of the light bulbs and then we see them being in 0, 1 state. In this case, we do receive information. Since two-state systems are used often, the second case scenario corresponds to us receiving 2 bits of information. But what if we have 3 light bulbs? Each one of them can be in on or off state. There is a total of 2 times 2 times 2 or 8 possible states. If we extend this logic to a system of n number of bits, we obtain 2n possible states and this number will be the maximum possible messages to be sent. Each message is a subset. And again, since 2 times n becomes considerable number very quickly, we can use the logarithmic function with base 2, which characterizes the set of elements again, and is more comfortable to work with. I should mention here that logarithm of base 2 gives us the number of devices, each with 2 bits, as an effective measure of information keeping capability. The examples we considered so far correspond to a discrete channel. That is an information system where you can have infinitely many numbers, but they are unnumerable. So imagine that we read n bits without knowing what they are. We can conclude that we've received n bits of information. But in case we know the states of those n bits, we receive no information. Okay, so how about if we pose the question like this? Let's consider that we know that 4 of the bits are before we read the sequence. But what we don't know is what the other n-4 bits are. So, how much information will be received if each one has 25% chance to be 1? And to answer that question, what we need to do is to predict the next bit. That is what Claude Shannon did in his entropy theory. The simplest way, of course, is to pose questions. Not random, of course, but what we need is to determine the minimum number of yes-no questions we must ask. So, if we can enumerate the bits from 1 to 4, knowing that each bit has equal percent of chance to appear in the most logical question to ask, is one that will divide the probability in half. So, we ask, is it the first or the second bit? If the answer is yes, we can eliminate the third and the fourth bit and continue with the next question that would be, is it the first or the second bit? And after this second question, we would have correctly identified the bit. So, in this case scenario, 2 questions are required in order to correctly identify the bit. Claude Shannon calls this a measure of average uncertainty or entropy, and it is represented by the letter H. Entropy is the summation for each bit of the probability of that bit times the number of questions. Now, the question here is, how do we express number of questions in a more general way? And as we've seen, the number of questions depends on how far we are. In our case, we've had only 2 questions, so we can say 2 levels. And we can say that the number of questions equals the logarithm base 2 of the possible outcomes of that level. And the number of outcomes at the level is also based on the probability, where the number of outcomes at the level equals 1 divided by the probability of that outcome. And that gives us the final equation. Entropy is a summation of each symbol of the probability of that symbol times the logarithm base 2 of 1 over the probability of that symbol. Shannon writes this a bit different, which just inverts the expression inside the logarithm, which causes us to add a negative. But to summarize, entropy is at maximum when all outcomes are equally likely. And every time you remove away from equally likely outcomes, or in other words, you introduce predictability, the entropy goes down. The main idea here is that if entropy drops, this means we have to ask fewer questions in order to guess the outcome. So far we spoke about discrete channels. That is a system where you can have infinitely many numbers, but still they are enumerable. But what if we ask ourselves how many numbers there are in the interval from 0 to 1? The possible answers here are 2, 0 and 1, and infinitely many numbers. How is that possible? Let's take back the example with the English alphabet. In the discrete channel example, there are exactly 26 possible letters and each position can only have one of those numbers. We can say that A is less than C with the correspondence that A equals 1 and C equals 3. And so we can order the 26 symbols and call A the smallest and Z the largest, for example. In this continuous channel example, this is not possible since apart from the numbers from 1 to 26, we have infinitely many in between them. And now the possible words will be infinitely many, even if we restrict ourselves to the one-letter case. Another example of the relation between the two types of channels is the following. Consider two switches such as that switch 1 is a simple on-off device and only have these two states, while switch 2 can continuously move between its on and off modes. The complete configuration space for the first switch consists of just 2 points, 0 and 1, if you remember the light bulbs, while that of the second switch consists of a whole line segment from 0 to 1. The points 0 and 1 and all of those in between them are infinitely many. In a sense, the continuous case has infinitely many more possible states than the discrete case. In practice, however, there will always exist some measurement error which limits our ability to work with truly continuous systems and effectively makes every system discrete. For example, we cannot differentiate between two positions of the microscopic switch which are just a few micrometers apart. We will see that the concepts of discrete and continuous functions are very important. We will also see that we can go between the two with certain accuracy and that both are crucial for antennas and communication in general.